Good evening to all of you. Hello.
Good evening.
Good evening. I'm Kamala Gunwadana. I'm a council member and I'm chairing this knowledge sharing subcommittee of Civil Engineers Sectional Committee for this session. So we have already we have done a lot of many number of webinars and presentations. They were technical and non-technical on most of the Tuesdays, Wednesdays, and Thursdays. So today also Thursday, and we have chosen this technical presentation. And today's presentation is under the title Seismic Design of Building in Sri Lanka, Eurocode 8. It is a timely, appropriate subject area that you will entertain right now. Actually, this is like a transition period of Eurocode and BSN to Eurocode. So Dr. Pradeep has taken the challenge and the responsibility to introduce you in this form, in this forum actually. And if these forums are not that effective, we'll see. Actually, we want to make this very much effective, and we'll see what Dr. Pradeep can do in the coming months. So let me introduce as a formality, let me introduce Dr. Today's resource person. Actually, knowledge about this area. So even though no introduction is needed, but as I said, always I have to give this introduction as a formality and a very simple way. He's a product from the University of Ruhuna. He has earned his bachelor's of civil and environmental engineering degree. His postgraduate diploma PhD at University of Basra. Is presently a senior lecturer at the University of Open University and Department of Civil Engineering. He's also the director, CEO of the ECO International Engineering Consultants Private Limited. From that also he's taking a big responsibility and he's giving hands to the young engineers. So I saw recently also he has done very good, given some appointments for young engineers. So all the young engineers can get the assistance from Dr. Pradeep. So also I actually, before I hand over to the Dr. Laxi, Pradeep, I hand given to Civil Engineers Sectional Committee. He has done, I think, few lectures, few webinars, address the public as well. So it was a very good input from him and we appreciate that. And also, I think we expect him the same assistance in the coming session as well. With his more than 12 years experience in the academic and industrial on high-rise building and bridge engineering and any of structural engineering and seismic engineering with many other major discipline areas. So including renewable sector and some green construction. So many. So I'll stop at this point and I'll invite Dr. Lux for the
Right. Thank you very much. I hope everyone can hear me very clearly. And I have one request. I think if the host can make me also as a host, so that would be better because the host bandwidth is much less. Can you confirm from the participants whether you can hear me properly? Yes.
Yes, sir. We can.
Yes, yes.
Okay, okay. So I think somebody can make me as also the host, so then there won't be any issue. So let me give a brief
Yeah.
introduction about the session, and thank you very much for the always the kind introduction. Actually, we thought of having this title because as Miss Camilla said, so we are right now in the transition period that was initiated 1995, the Eurocode, and after later on, the latest revision also came the 2010. So it's like 12 years back. So the issue is especially all the universities are moving with the Eurocode 2, 3, and the 4 progressively because we have done the national annex and all. But when it is come to the seismic, so the earthquake, so we are much I would say the consistency of the design is quite to be improved. So based on that, I will today give a flow chart especially to the design, because I mean to discuss with all the analysis and the design, it takes like 3-4 weeks. But however, if someone missing the fundamentals and the way of designs, again the seismic engineering will be discussed today. So as you know, the Eurocodes consist of so many chapters, and it's not like the BS codes. Let me take a 2-3 minutes to explain why is it. So the Eurocode is a combination of the design guidelines, which is basically focus on the performance-based design. When you talk about the BS code, it does not provide a much freedom to design and decide by the engineer what the local requirements can be applicable for the design. So in the other hand, so in Eurocode, the word you always heard is a national annex. The BS code, when it is developed, so they have focus on their territory and their country. However, when the Eurocode is developing, so the design team has focus because most of the colonial countries are adapting this the code for their design. For example, if you have done any design for the Maldives, so still they are working on the BS. For the Sri Lanka, so we are using the BS and the Eurocode likewise. But the country like India, so they have a own code. But if you clearly see the equation comparison in between, so it's basically gives a same design principles, I would say, right? This is the basics of the code of practice what we are. So I would say though, if someone asks what is the major difference in between the BS and the Eurocode, I would say the BS is the code based design which has been converted to the performance based design in a Eurocode. In other words, so you can't work with the single code. That Eurocode 2 sometimes refer to Eurocode 7. Eurocode 7 is referring to Eurocode 8. Likewise, all the codes are interrelated. In the BS code, it is not much. So it doesn't talk to next code which is available for the design. So let us move to the slide. So if you do have any questions, I prefer to see in the chat box. So at the same time, I will try to answers those. Let us talk about what this seismic action. The seismic loading is the matter of the energy release. We know entire world is having the different plates. So if you take the planet, so that is having the different plate of a movement. So each plates are moving each other. So likewise, so in the below this movement, I hope everyone can see it. So here what will happen is when the loads, the plates are applicable in likewise, right? So during this movement, so the energy are accumulating in this position, right? So the accumulating energy become absorb up to the maximum energy which can absorb by the plate. So it is right times to dissipate the energy. So it's depend on the direction what it goes. So the earthquake basically start from that. So that is the basic way of earthquakes are forming. But there are certain percentage, very less, 1 or 2, even less than that, due to the artificial man-made activities. So for example, in China, 2-3 years back, there was a huge soil cut and loaded into the next adjacent land for the nuclear plant. So there was then the liquefaction. So we call it's not a landslide. So what will happen is, so in the both side, the pressures come in one direction. So then the liquefaction is taken place. So then the waves start, and that will be propagate to the land side, right? So this is what we call the earthquake. But for us as an engineer, this part doesn't, do not need to study, because the earthquake magnitudes, it's immaterial for the structural design. Because I would say the earthquake loading is the one which is not repeatedly common as it is. If you take the left hand side, sorry. So this area, so you can see the acceleration, and the second one is the velocity, and the third one is a displacement. None of these curves can be coincide to the any of other earthquakes. So then how we define the earthquake loading is something different. For example, when you design the building, especially static loading, you consider live load, dead load, so whatever, if it is hydraulic loads, so any of loads can be determined, and it can be quantitative by the calculation, which earthquake will never able to do that. Because the earthquake, what will happen is, in the earthquake which is coming yesterday may not be coincide with the today. What we are doing for that, what we are trying to do is, we are taking the results of this worst earthquake and we put into the time history. So it can be in terms of displacement. So for example, if you refer this one, so it is with the displacement. This is a time. So the next one is it is with the velocity. So how this is a second order equation. So we will come to next slide, right? So the another one is acceleration. But fundamentally, you need to understand few things. When we use the general softwares like a SAP 2000, ETABS, beyond that the MIDAS, so whatever the general analysis softwares will not support much for the dynamic analysis. Why is it that? Because we may not be able to produce each and every loading conditions. In any softwares is running by the iterations. When you apply the load, so then it is convert to the load stiffness, and the load stiffness will reverse calculate to the force. In any software in the world can be categorized into two. One is a force-based analysis and the displace-based analysis. So most of the general softwares like SAP 2000, whatever you use, the ETABS, MIDAS, are basically based on the force-based displacement. So in other hand, so if you take F is equal kx, so you give the force, so the software will calculate the stiffness of the material stiffness, and then it gives the displacement. By displacement, there are so many ways to find it out, because displacement is a function of the movement, rotation. So I think if you learn the undergraduate, so the movement, now when you are flexural equation writing, so then it is a function of the theta, which is rotation or the displacement, etc. You can written it out. Based on that, you will get it. But however, what the software, general software issue is, this F is a constant. So if you change this F with the time, the software will not be able to make a iteration. Iteration is the steps, the load increment. If you take a 10 kilonewtons to be applied, so the 1 kilonewton, what will happen? 2 kilonewton, what will happen? 3 kilonewtons. So likewise, the dynamic load, which is referring to the time, need to analyze. So general software may not be able to do that. So that's why we usually do is, so the dynamic load, we convert into the quasi-static loading like this. So you have a, with the time factors, this is a time, this is the force. So if this is the curve, what we do is we convert this into the quasi-static loading condition. It means we fix the load for the certain time, and then only you can give it to the general softwares. But there are certain software like NCs, the OpenCs, right? That can be make a lot of iteration because it is not working much on the graphical view. Then the graphic will use to the iterate and do it. That's how the earthquake analysis is very popular in the DOS mode rather than the graphical mode. I hope everyone understand how the earthquake is working. So the earthquake is a dynamic load and it is working with the acceleration, right? However, as a design engineer, so we make into the static, quasi-static loading condition because we are not be able to analyze in the general softwares. So on the other hand, so what will happen is now we know in any designs, any type of design. So people might ask, so what is the best definitions for the design? So the my definitions for the design is any structure is a balancing of the external energy and the internal energy. Even the high-rise building, if you do the static loading, right, or the dynamic loading or whatever, so there is a work done F into delta. So the beams are bringing down. So if you are done the potential energy, for example, if you have a high-rise building like this, so let's say man is rising up to this level, the 10th floor. So he brought it up the energy mgh. That energy should be absorbed by the building. So how is it absorbed? Because this slab to be, so the beams to be taken care of this, because then the beams is taking the theta and it deflection delta. So then F into delta, so the work done calculated, that has to be equal to the work done by the external force. This is what we do as a design. That is where the fundamental is started. I think if someone much interested on this, how the design equation are formulated, so better in 1980 to 1990, there are so many papers and the book written by the Mander. He's a guy from the New Zealand. So he is the guy who initiate these energy balance things to the code of practice. So similarly, what we are doing is in an earthquake, also trying to balance the energy in two different ways. One is a local and one is a global. So I will talk those things in the separate slide. Before that, we need to understand. So this is the normal design force. So what will happen is with the time, it's increased. So we assume that it's the materials are elastic fundamentally. But in reality, so it won't be happen because most of the material in the world is neither plastic 100% or behavior or the elastic behavior. So what we are trying to do is all the material in between, we are convert into the elastoplastic material. That's how the steel are converted like this, right? So the concrete is like this. So initially we take it concrete, the reinforced concrete as the elastic material. Later on, it convert to the plastic. And beyond that, the concrete behavior is much different from the steel because we know the concrete is good in compression, but not good in tension. But it's steel in other way around. So the good in compression and the tension and both. Then what will happen is, so I will come to this peak acceleration and those things later. So this is the elastic spectrum. So our spectrum, design spectrum, always to be below the elastic spectrum, which is given by the analysis. Then in earthquake, we have a fundamental understanding of the energy dissipation should be taken care of critical region. It means, remember, now when you take the high-rise building or any type of building, let's draw one high-rise building like this. If you have any questions, so I'm really happy to answer on the same time. So remember that earthquake took place. Then the building is starting taking the dynamic load. In other words, the energy which is induced by the earthquake and it is taken up to the building. So then this is how the Eurocode fundamental is working. So then the vertical side, the energy is taken up by the building. So building start shaking on the both line.
එතනක බනින්නේ ඒක එතකොට දැන් එනං කියන්නේ නිකන් කාලේ අපතනේ يعني බොරුවට ගිහිල්ලා ඉවරලා මෙතනට වෙලා බලන්න.
I think we can hear you. You have to mute Dr. Mrs. Kamila.
හරියට සුපර්වයිස් කරන්නෙත් නෑ බලන්නෙත් නෑ මුකුත් නෑ අන්තිමට.
Right. So so this is how it is happening. So then what will happen is, so the initial elements are the foundation and later on it takes by the column. Right. So the column and it transferred through the columns to beam. This is how it is happening. So this is the unique load that is working from the ground to up. And all other loads you are taking like a dead loads, live loads, or any other load, name it, including the wind, which is carried top to bottom. But this is the unique load which is carrying bottom to top. So we have to be very careful because these columns are we name it as a primary column in the earthquake engineering. To take care of this primary column, there are certain ways to do it. One is we have to see whether this lateral drift, which is taken care by the different kind of modes. We know in any building, right? If you lump the mast in the different floors, so there can be a different kind of modal analysis. Let me quickly draw that. So maybe this is mode number 1. The second one can be like this. The third one can be like this. So we know what is the fundamental time based on that, right? Then especially when the earthquake, seismic are considered for the designing, having this modal analysis, any structure, not only the building, not only the bridges, any structures, much important to identify by the engineer how many modes to be considered for the earthquake engineering. This is a fundamental. However, we know that this maximum drift happen in the mode number 1 will be given a higher base shear. So that has to be calculated, right? So I just wanted to explain you here as an engineer, especially these joint. These joints are much vulnerable, especially the columns, beams, joint, right? These joints are much vulnerable. However, the effect of this loading going ups is getting reduced, like the vulnerability of failure is getting reduced. So we have a few ways of design these nodes, like columns and the beams. We assume, I think in the right hand side you can see this graph. The first one is let me clear this one a little bit. This graph, you can see when you applying the load, right? The first one is when the load is starting applied with the displacement, the plastic hinge starting point of column beam joint. Okay. Then what do you mean by these plastic hinges? Plastic hinges are usually defined as, so the point where it has gone to the maximum level of energy accumulated. All right. So the energy accumulate, the joint are gone for the maximum energy capacity. Energy accumulated in the joint are reaching the maximum capacity. So then what we'll do is, so these plastic hinge, for example, if you draw the, sorry, if you draw the maximum energy accumulation, somewhere here it was reached. So then it was transferred to the beam side. In the second one, you can see the energy, the point where the plastic hinge are formed, it was pushed to the beam side, not the column side. In the third one, still next flow, it is pushing to the beam side. So this is what we call is the strong columns and the weak beam concept. I will explain why is it important and how is it important in the design process, because we know we have two ways of designs. One is a local design and one is a global design. So one questions asked from the audience with the raft design, how it is vulnerable. Because the Eurocode 80s advise us to take care, because raft is a long element which is connected by all the columns. So it is considered as a rigid foundation. So then it was now, for example, I will come to that point at the later stages where the detailing is discussed. However, we need to detail the primary region. So define of the primary regions in the raft is much different from the pile. So this is how the changes is coming. But when you are designing with the raft foundation, I didn't add this presentation. There are two types of analysis to be done. One thing is overturning. Overturning you do for the lateral loading as well, but then the overturning checks to be done for the seismic as well. This is the unique, the differ for the check with the pile design. But however, there is a difference between the pile design, pile buildings and the raft buildings in terms of the detailing. Let me quickly go through this response spectrum analysis. I think most of the engineers are following, starting with somewhere here, this soil types and all. This is where the engineers are starting doing the design. But if you clearly refer this earthquake engineering design, it is not somewhere to be started. It is somewhere started to be with the fundamental time. That's why I said to you, the model analysis is much important in the earthquake engineering. If you don't do this part properly, so then your earthquake analysis for the particular country and the particular soil condition will be completely out. So I think the number one, if someone doesn't have much understanding about the response spectrum analysis, you need to carefully understand how it is applicable for the seismic engineering. And here I will take you a quick explanation of two different kind of structures. I'm sure most of you haven't heard this one, because when you are detailing in Sri Lanka or wherever according to the Eurocode, we are much talking about the energy dissipated structures. But remember, in the Eurocode, it's entertain non-energy dissipated structures. So what do you mean by this non-dissipated structure? So to dissipate the energy, we of course we know that we need some kind of structural movement within the building. So for example, if you take a bridge, now like these are the piers, right, and beams, etc. If not only this is not only for the bridges, but buildings are not recommended. Likewise, it's written in the Eurocode. You can decide any type of structure. One is non-energy dissipated structure. Other one is energy dissipated structure. So energy dissipated structures I'm going to talk hereafter. So that's what the table is here. It is. So non-energy dissipated structure is the Q basically less than 1.5. So you might ask, are there any structures like that? Yes, very rare. In the Eurocode, it says if some horizontal structure, especially like a bridges, if the bridges or any other structure which can go for the higher order structures in analysis, so you can consider this analysis, right? So even the Q is equal 1 to Q is equal 1.5, you can use it. What kind of structure? Especially like the bridges, the code itself use the word also, the cable stray bridges. You know, this kind of structures are allow for the horizontal displacement and the vertical displacement as well, because vertical displacement, because it is the main elements are working on by the tendons. The tendons can go through the horizontal and the vertical as well. So then we call those kind of structures is a higher order equation. So higher order in the equation, the more higher order model is movement is the structures can be designed as a non-dissipated in structure. So let us quickly discover what does it mean. It means when you apply any external loads to the structure, right? Any external load is in a short term, the entire structure will be react against that. So the energy will be start accumulating in all the tenders, all the elements likewise. But when you take a buildings, it won't be the places, because building are designs for this concrete a certain level of brittle material. Wherever cable straight are the higher ductile material. So then the transfers of these energy to the structure will take longer time. So that's why if you see this table, it doesn't recommend more less than 1.5. Even the 1.5 is only for the inverted pendulum system. So all other systems are more than 3. So the alpha U and alpha 1 is a matter of the loading arrangement where the geometrics come. So the approximately this value may be the 3.9. This one maybe go up to the 4.5 to above. Then someone could ask, the biggest question in Sri Lanka is asking whether do we need to design against the earthquake. So that question everyone is asked, because we are not much vulnerable to the earthquake. The Eurocode does not talk about the the vulnerability of the earthquake. Eurocodes talk about basically two different kind of ductility level, and including the limited ductility, it is 3 different kind of ductility. First one is a limited ductility. The second one is a medium ductility. Other one is a high ductility. So when you design the buildings, of course, you have to start with the medium ductility, because we are not entertaining the limited ductility. But some kind of structures like the bridges, the dam, so of course you can go in this direction. All right. So then mostly people start working on the seismic engineering. The main phenomena is AG, where the peak ground accelerations come. Remember, peak ground accelerations nothing to do with the structural detailing of the seismic. This is what the fundamental understand. There are 2 types of application in a seismic engineering. One is in the detailing, one is the design. We know this is the equation in the dynamic analysis. So it is a function of the acceleration. When the accelerations come, right? So maybe you can take off this one, or also it is a function of the velocity. Finally, this is the force. We know that from the F is equal ma. So here the U double means the acceleration. But Eurocode does not support any kind of acceleration in analysis. Even the wind, still it is entertaining the 3-second gust speed, or else the static loading condition. Right? But when it is come to the Australian code or the New Zealand code, it is entertaining the acceleration. So that's why I think some of the structural here in Sri Lanka, engineers here in Sri Lanka are preferred to do the wind and wind, especially according to the Australian code. So for me, if someone asks what is the best better, so it's depending on the geometry of the building. But however, if someone asks what is the most accurate one, because in a reality, since the wind and earthquake are the dynamic loading, so that has to be deal with the acceleration. So the similarly in earthquake also the same things happening. But however, now when you are talking about the reinforced concrete in the Eurocode 2 or the steel design in the Eurocode 3 and the composite design in the Eurocode 4, it does not talk about the two different classification, which is detailing and the which is design. The detailing of the earthquake is nothing to do with the seismic activity. It is like a request what you are doing in the Eurocode 2 to comply what you are doing in the Eurocode 8. For example, it does not cost for the client, it does not cost for the structure. For example, let's say you have a column like this. If you say fundamentally, you find instead of, let's say this ASC steel area is, let's say 1200 millimeter squared, which is required, right? So in a Eurocode 2, you can even put the 4 bars depending on the diameter. But if you refer to the Eurocode 8, you may not be able to do that. Minimum BI there, you have to put another 4 bars. So then the steel demand is this much, but there is a minimum value for this BI in between the 2 bars are here. Eurocode 2 also that limitation is there. The similarly Eurocode 8 also that limitation is there. Whichever minimum you have to put into the element. So this is what we call the detailing. Detailing is nothing to do with the Eurocode 8 or the Eurocode 2. It is a matter of you are working in 2 different code and you can provide the same steel area, but compliance with the Eurocode 2 demand and the Eurocode 8 demand. I hope everyone understand what I am saying. Even how you put these transverse reinforcement. Now we know that the Eurocode 2, the transfer reinforcement basically work with the shear design, shear capacities. But when it's come to the Eurocode 8, transfer reinforcement are basically against the ductility, design of the ductility level. All right? But similarly, what I was telling to you before, the transfer requirement, this is similar. So you no need to put the separate 2 different transfers, which is coming to the shear and which is coming to the ductility, and you no need to sum those things. So whatever the reinforcement you find, the transverse reinforcement you find in the shear design, and whatever the transverse reinforcement required in the ductility, right? Whatever largest requirement has to be put into the element. So if you do the right detailing, sometimes, because the number of the leg required for the shear calculation, but ductility, no need a number of the legs or etc. It is a matter of the passive confinement. It shows how much you put the volumetric ratio of the transverse reinforcement. It in other words, if you take a column, 2 shear links are like this, right? Within, I think I kindly request everyone to mute yourself, right? So then 1 meter of, 1 meter cubes of concrete, how much you put the transverse reinforcement? That is, we call the volumetric of volumetric ratio of the transverse reinforcement. And this will be multiplied by the Fy times Fc. It means Fy is the yield strength of the steel and Fc is the yield strength of the concrete. So on the other words, it says, so this is steel area, this is concrete area. So how much proportionately you put the steel stress over the concrete stress? That is what we need in the ductility. So then in other words, the transverse reinforcement in the Eurocode 2 is facilitating to the shear. I think if you don't understand, let me, please let me know, but quite difficult to understand very first time. So what I am saying the same now, if you are a smart engineer, if you are the smart engineer designing, pre-design the section sizes and the transverse reinforcement, right? It is like a integration of these two. So then the selection of the sometimes the element sizes, right? And the main reinforcement and the transverse reinforcement will economize the section. So how you do it? So basically developing two, I don't know, Excel sheet or something, and for the Eurocode 2 and the Eurocode 8, same times applicable for this one. So you can save a lot of steel, right? Especially on the transverse, because with the Q factor increasing, so the structures become more ductile. When the Q factor is reducing, so structure is moving towards to brittle. So what we need is having the same set of the transverse reinforcement, right? To reduce the, increase the stresses which can be generated by the transverse would be help for the ductility as well. So the design, again, the ductility is not something different. It has to be do with the Eurocode 8 and the Eurocode 2 at the same time. If you work differently, so your section won't be economical as you think. Very quickly, I wanted to show you how this is work in the ductility level fundamentally. But these values are depend on your soil condition, especially in the country. So we were talking about two different ductility, right? So this one, low ductility, is basically for the non-dissipated structures. These two are dissipated ductility. Here we call this a ductility as a 1, right? So the low ductility level. Others, the equation are shown in here and here. Two different equation. This is for the square columns, rectangular. This is for the circular. But I just wanted to show you off, right? Especially, I took here to compare the few countries' code of practice. So this is a New Zealand code, right? This is a New Zealand code. This is a Euro code. This is a Italian code. So the Italian code does not give any equation. It says the minimum you have to put this one. But Euro code, because Italy also adapted the Euro code, but they have a national annex because Italy is much vulnerable for the earthquake. Look at the New Zealand equation. So here 5i over, this is the 5 ultimate over yield is the ductility mu. So this equation mu is here, right? So the very similar equation, you can easily convert this equation to this Eurocode 8. So I simply say the Eurocode 8 is adapted the New Zealand 3101 approach. But however, the Eurocode 8 make very simple this equation in a different way, because in a earthquake engineering, there are 5 variables are affecting against the ductility. One is the concrete grade. The second one is a steel strength. Third one is a transverse reinforcement diameter and the amount of transverse. Fourth one is a longitudinal reinforcement and the there is stress. Fifth is a geometric shape of the element and the sizes. So with changing all these 5 parameters in this equation, I think you can see quite, I would say the most complicated equation in the code, Eurocode. And if you take any code of practice of the Eurocode, this is the most complicated equation that you have to deal with. And it more than this, it is complicated the New Zealand code, right? We don't need to study on the New Zealand. So here, right? Here it shows so many parameters. So the alpha is the geometry of the section. Omega W is the volumetric ratio of the transverse reinforcement that I was discussing with you. So that depend on the 1 meter cube of the concrete, how much reinforcement you put in terms of the F dash over Fy, right? So the second one is the axial load ratio. If the column having this axial load, we call it a VD, right? VD is defined as a NED as well. So this is a P over area of the columns times F dash C. It means 1 millimeter square of the surface, how much going to take a load as an axial load. So this value, sorry. So this value, is N is 0.1 to N is 0.7 is recommended. So let me quickly brief why it is more important in the ductility design or the earth seismic engineering design. So if you see this equation, right? If you this equation, VD is the proportions to the ductility, inversely proportions to the ductility. If you put the mu somewhere here, it comes 1 over mu D and times VD. So finally, you can say 1 over media. So the ductility is inverse proportions to the axial load ratio. That you should understand. I think it is very much clear. We can understand from the fundamentals where how it is applicable in any structure. Let us see. Let us get there is a column. There is a column, right? So we give like this displacement. So it means it goes here and coming back with the N is equal 0.1. So it means a low axial load ratio. At the same time, the same column N is equal 0.7. I think we can put like a 50 kilonewton or the here maybe 400 kilonewton. Forget about it, right? So the same displacement. So what will happen? Actually, if you take the drift of these two columns, how much it sway, if it is delta, of course, this is delta 1 and delta 2. So delta 1 is much higher than delta 2 because it has been given an axial load, the high axial load, here low axial load. When you have a columns, right, you give the loads and you are trying to move itself, it's hardly move toward the horizontal direction. So the same thing happen in the earthquake as well. So if any columns having the higher axial load, then the column won't be move much. Then the issue is if the column is not moving much, what will happen? So the force is the horizontal earthquake force is, let's say, Fe. The displacement is delta, right? So in this you can refer this curve. So the delta somewhere here when the axial load is high. So work done within this area is lower. In this case, case number 1, so the displacement is higher. So the work done is much higher. Then the work done is lower in the sense that the structure is brittle. So structure may not be able to take a lot of energy. If the structure can move further without any failure, we call it a ductile. So in that case, in a lower ductility, the lower axial load, so the demand for the ductility is lower, because when you apply the same load, it's go for the higher displacement, higher horizontal displacement. So the work done in particular column is much higher. When you have a higher axial load, so the same column with the higher axial load, same displacement, same force, so it will not go as the case number 1. So then the work done is much lower. So then in that case, demand for the ductility is much higher. What we have to do in here, you have to put lot of transverse reinforcement. Here, less transverse reinforcement, because you have to push this one to here. Because here work done. Now in that cases where you have taken this one somewhere up to here, right? Here somewhere up to here. That is the biggest issue in the earthquake. So earth design again the elements which is under the compression loading condition. So if someone asks, so what are the hint you can give? What are the thumb rule that you can make your section economical, etc.? So I would say basically your axial load ratio, axial load in the sense, if you take a column, if you take any column, this load is P. So you can get by the software analysis, right? You can get by the software analysis simply. So this P over AC is a concrete area times F-CD, the design load, called the NED. In other words, this is a VD, axial load ratio. So this ratio, keep it in between, I mean less than 0.5. It is possible. It is possible. So then look at here, how is it possible? In this equation, the axial load ratio, look at, there's no steel part, which is only looking at the concrete part. But when we designs again the Eurocode 2 or the BS steel, so the axial load design in the column, we have a, if the column support to the axial load, I mean only axial load, let's say, no movement. So we have a 2 component, one from the, one from the load from the concrete and other one from the longitudinal reinforcement. So if you increase this part, because to bring down this axial load ratio lower, so what you have to do is you have to improve, because this is the NED in the column Eurocode 2. Let me write the equation properly, then you understand what I am saying. This is how you work with the 2 codes together to make the economical section for the resistance of the earthquake. We know that the column NED, right? So it is equal F dash, right? S steel yield into the AST, right? So you can put the safety factors, whatever gamma X, right? Plus AC times F dash CD and the gamma C, the safety factor. So according to the Eurocode, I would say if you, I mean, always you try to have a bigger portion to this and have a minimum portion to this, maybe the 70 to 30, etc. So that's depend on the element. So if you increase automatically this value, it is automatically support in the Eurocode 8 to reduce this NED. But if someone take the 50% this load, so this automatically this NED is going up. Then what happen is in the same column, same size, right? The longitudinal is okay. You have to put a lot of transverse reinforcement, because if this VD is going to up, so the omega W is going up. I hope everyone understand what I am saying. So this is how simply is this reason why high-rise buildings are almost conical in the pyramid shape and the lower axial. Yeah. No, that's not the case, right? So that's a different thing. So I will answer to that question, sir. This, I think this is what I was telling to you. Every engineer should understand the Eurocode 2 and the Eurocode 8 together. So very easy to detail. So there are few equations that you works with the other line. I hope this is very clear for everyone. So make the axial load ratio lower. Then of course the axial load ratio is lower. When the axial load ratio is going down, automatically the required transverse reinforcement at the critical region. So we will discuss where the critical regions come is lower. Like, okay, so this is the detailing of the column where we come. So these are the critical region, right? So that now earlier side we were discussing these omega WD. Omega W is the reinforcement ratio. I will talk in another lecture. How do you calculate this omega D? So today we don't have much time to discuss it. So when you calculated this omega T, that has to be provided it somewhere here. So if you see here, this is the critical region. This area is a critical. This area is a critical. This is a normal area, right? So detailing of this area, if you not properly manage the geometric size of the element, so you need much higher volume of the reinforcement. In my experience, some of the high-rise building came to me for the review, right? So statically in the Eurocode design 2 is perfect. But what was happening is, having not considering this axial load ratio, they have designed again the Eurocode 2. Then they go for the Eurocode 8. Then when you are going for the Eurocode 8, so you haven't thought of VD, axial load ratio, N over FC times AC. Then you have no choice. This N, you are unable to change it. The size, you are able to change it. Then the VD is coming 0.7, 0.8. In Sri Lankan, any elements that you calculated this one, the VD is much higher. So then you need a lot of reinforcements to be satisfy this primary region. To make an economical section, in every engineer should start with the Eurocode 2 and the Eurocode 8 in the primary size in the element. Someone asked whether we need to design again the Eurocode 8. Of course, yes, because Eurocode 2 said, the Eurocode fundamentally said you have to comply with each and every codes. But the BS is not like that. So if you need to satisfy with the Eurocode 2, Eurocode 7 and the Eurocode 8 together, so then the better approach you should take, especially in the sizing of the element. Your reverse calculation won't be here make much. So this is what I was telling to you. In any columns which is under the critical region does not allow for the 4 number of bar. It has to be 8 number of bar. Because there is a restriction for the BI. I can explain why is it also. Because if you take this one, this element, right? So we know that what in the column section, if you put the transverse, if you apply the loads, axial loads to this direction, right? So it is starting the active pressure generated on the each direction. So then the hoop is making the passive confinement to this direction. To make an effective passive confinement, this, if you put 2 legs of this, is not work, because this element concrete, if you are starting giving the active pressure to this direction, concrete doesn't know how it should be behaved. So they start cracking inside. Then if you put these additional ties like this, even you can put ties like this is okay, right? So what will happen is, when the concrete is starting having the active pressure every direction, so it is meeting with the steel. So what will happen in the certain level, if you take any stress, any shear distribution on this line, so it is uniform. It is like a uniform. But if you don't have now this element, right? If you take any shear, right, the normal shear, what will happen is like this, the concrete is starting shearing. But if you put additional like this, so that it is reducing this. The same stress they are managing with a different, because we know that the concrete, however, in the BS code, either Euro code, it says the concrete shear, not the steel shear. The F dash C is equal 0.8 times F dash C. Sorry, VC, right? So even if you put here, let's say if you put 25, it is coming 4 megapascal. Let's put 50. 50 is almost, let's say, the 49. So the 7 times it's still coming the 5.6 megapascal. Even though you double the 25 to 50 concrete grade, but the shear increment is 4 to 5.6. It's now you increase 100% to the concrete strength, but the shear improvement is less than 50%. That's why the Euro code has, I think, I don't know whether you have noticed it, does not allow to go even to the maximum shear capacities of the concrete more than the 50 megapascal, because Euro code doesn't value the much on the concrete shear capacity. If the concrete FCD is greater than 50, right, up to the 50, they comply this 0.8 times F dash C. After that, 1 minus FCK over gamma. So it means even this equation, there is a portions to be taken off. I will quickly tell what is the reason for that. Because up to 50 megapascal, concrete usually fail through the cement paste. What do you mean by cement paste? If you test the concrete test cube, you have aggregate like this. Then you have a concrete paste like this, right? So up to 50 megapascal, so the failure mode will take through the concrete phase, like concrete failure. Above the 50 megapascal, it fail through the aggregates. So the aggregates has a much varieties in the world. That's why it is not encouraged more than that. More than the 50 megapascal, like a high performance concrete, like 100. I think I'm not sure whether how many of you have seen the cube crushing. You see the aggregates are fail, not the concrete paste. So this is the biggest issue we do have. That's why the Euro code 8 does not given a much freedom to get the concrete grade as it is. So restriction of this shear will definitely affect to the detailing of the reinforcement. Okay, so let me quickly, I think the time is going much faster, right? So this is one detail. So I was telling to you normal axial load ratio in the DCM keep 0.65. In the DCH, this is a ductility medium, this is ductility high. Look at 0.55. So when you reduce this one, the ductility, the ratio, the requirement of the transverse omega WD is getting down, because axial load is coming down, omega W is coming down. Omega W is the one directly proportional to the transverse reinforcement. So a lot of transfers to be put, otherwise to make a section ductile. So let us understand this fundamental, how it is work. Other than that, everything is fine. So these detailing and everything, it's matter of you work on that. So the what is the DCM maximum critical shear length? So the you can see here 0.45, here 0.6. So the like if you take floor to floor height is a 3 meter, here 0.6, like 1.2 meter you have to take in as a critical region. So if you mean out of 3 meter 1.2, so like almost 45%, let's say 40% to be considered as a critical region. That's how it's work. I will stop from here, from the design. So these are the demand for that, putting into the one table, right? So here the equations are similar. So in addition, when you put this one, you can find it out the shear failure angle theta. I remember if anyone has working on the foundation design according to the Eurocode, so they were actually looking for the direct shear, punch in shear, likewise, etc. So here in the foundation, the shear mode is calculation. What is the theta of failure? Similarly, it do in the concrete as well. But we need to make sure we need to make sure that the failure corner is much higher than the allowed corner in the angle in the concrete, that I will be leaving to you for study. So the cot theta usually, I mean, greater than 2.5 would be fine. So that is what it written in the here, right? I was just telling you, usually when you model the concrete, when you analyze the concrete and the detailing, so these requirements are satisfied usually. But however, it is our responsibility to check that. Now we have done the local analysis, but now that is not enough. Now we are coming to the capacity design, right? So if someone, I will quickly finish this one. If someone in any lateral load, earthquake or the wind, if the structure is trying to develop the plastic hinges at the column, so the column start failure. So then easily what will happen is a global, before the local failure, the global failure will take place. This is called the global failure. So if someone's allowed to design the beams for creating the plastic hinge within that initially, after that it goes to column. So that is, we call the global design, because here it is not failure any columns first. So that's why I initially also earthquake is very believe strong column and weak beam concept. If you have seen any structures in the Europe, right, or the earthquake attacks building, which is designed against the earthquake, you will see a lot of walls and the beams are failed, but not the columns. I think tonight you can see on the Googles, whichever remaining structures, which is a fundamentally the beams and the walls in between are failing, not the columns at the initially, right? So not to fail the column, there are certain ways. I'm not talking to, you can have the bearing, right? You can have a different kind of energy dissipated, mechanical, electrical one also. There are so many ways to do that we can discuss in another one. Now we have discussed about the columns. Now we are coming to the beam. We have a beam. I'm not sure how many of you heard. If someone asked the question on how many types of the beam available in the world and the entertained in the codes, there are two types. One is it is called the deep beam, that you are doing design against the Eurocode 2, whatever. There is another type of beam that is called the concealed beam. You probably call this as a slab beams as well, but it is not. The slab beams is nowhere it's code use that terminology. So it is called a concealed beam. The deep beam in the sense that, so the depth is much higher than the width. So in the concealed beams, width is much higher than the depth. Now you might ask a question, why we know this certain application you need to do that. Today I'm not going to discuss. So the concealed, when you design the concealed beam, what the code is saying, code does not say about the concealed or the deep beam, but some annexes say you don't need to much worry about that. You provide the on the other hand, concealed beam, usually bottom and the top reinforcement are not much deviated. This is quite a challenging statement, but anyway, that's how it's coming. The deep beam is different, it is different because when you draw the bending moment diagram or whatever, the sagging, the lower reinforcement higher rho, and here rho dash is higher. Here rho is higher. Rho in the sense that the longitudinal reinforcement ratio. All right. So what code is saying? This is the equation for the ductility. The rho max is the one which is in the below, right? If you are design the row max, right? So according to the Eurocode 2, what you are putting in the top is a nominal reinforcement. That doesn't allow in the earthquake design, right? So what you have to do is, let us consider the ductility level 10 or the 15 or 20, etc. So I will talk about the ductility demand on the another day. So then once you find these rho max, in the other word, AS tension, longitudinal tension. So rho max in the sense that AST over the area of the beam. So B times DE effective. This is how the rho max come in. So rho max is this one, right? So once you find these rho max, so you can't put here the nominal reinforcement. In the Eurocode 8, what is say? You have to go this equation from here to here to find it out how much you put in the top. Then the equation is rho dash. So rho dash you can take on the other side. Rho dash equals 0.0018 mu phi sigma yd times FCD over FYD minus rho max, right? So then the mu is, you can put 10 or the whatever. So others, you know, this is the steel strain, FCD, you know, FYD, you know. So having this one, the here how much rho dash you need to put. Rho dash in the sense that rho dash is equal ASC compression steel divided by the F dash C times area BDEF. B is the width into D into effective, right? So all these value you can calculate, and you can calculate this one. Then again these two, you know, in Eurocode 2 you have an equation to provide that. So if you balance this equation, it is a function of the geometry, because when it is come to the B and D selection, right? Sometimes you no need to put additional steel for the ductility if you are smart enough to select the beam D and B. Then once what you are doing in the Eurocode need to be satisfy Eurocode 8. If you are not selecting right elements, right geometry, and you finish your Eurocode 2 design and come to Eurocode 8, then sometimes unnecessarily you have to put lot of reinforcement at the top. That is the issue. And similarly here also similar critical region, right? These are the minimum requirements for the beam design. If you do have any question, you need to post it. I will quickly answer once finish this presentation. Right. So these are the minimum requirement A's and everything, right? This is what I am telling. Eurocode 2, Eurocode 7, Eurocode 8 is not a 3 different code. That is a single code that you have to work together. Similarly, Eurocode 3, Eurocode 7, Eurocode 8 is not a separate 3 codes that has to be work as a single code. Then the final Eurocode 4, Eurocode 7 and Eurocode 8, again the similar. If you are smart enough to work all these 3 together, you can make very economical solution for the high-rise building. The issue is usually what people do is they do against the Eurocode 2 and then they try to applicable for the Eurocode 8. So at that time, what will happen is once you decide these A's, Eurocode 2, and here A's is much higher because sometimes your section is lower, sometimes your diameter is lower, sometimes not even the reinforcement. The way you have put the reinforcement is not good, not in support to the Eurocode 8. So this is the same, all the equation and the fundamental that you are putting into the beam. So this is the equation, right? So the one day we can do how to design the ductility against the the Eurocode 8. But today I was given a flow chart of how you can work on the ductility and what you have to do against the seismic activity. So the seismic ponding that we are actually, I don't know how many of you know this one. So the ponding of the seismic activity also become very critical because our areas now, land plots are getting very small. Sometimes we put the apartment very close by like this. Right? Based on the model analysis, you can calculate the drift, right? So this drift is a function of the acceleration, right? I will do one day how to calculate this one. So because of that, sometimes this can be happening. This is called the seismic ponding. I'm sure 100% in a Sri Lankan scenario, we are not doing it. There is a reason for that because we don't find very close structure right now. But nowadays we experience it sometimes very close by. Okay, so that's the issue because sometimes even the 10-story buildings, 14-story building, you have to be very careful about the seismic. Not only the seismic, sometimes this is a matter of the wind as well. So the ponding effect, right? Ponding effect, it is much important to work when the structures are working on the blind. Then I'm not sure how many of you do the push-over analysis because push-over analysis basically giving you how to perform the plastic hinges in the building. This is a very simple way you can do is what we do is you have a high-rise building like this, right? So you lump the mass in each and every floor like this. So then K1, M1, K2, M2, K3, M3, K4, M3. Likewise, then you do the analysis in the model. Then you push it. Then you can calculate how much the base shear. So when the base shear comes to the maximum limitation, so we can find it as the plastic hinge where it formation. So better in any structure, you allow plastic hinge formation at the top. But however, it is quite challenging in any structure. So the first question asks someone, what will happen in the structure is having the raft and the file. Let me quickly explain that one. So we are running out of time. Right. So the thing is, there is a building like this. This is with the raft. The second building like this. This is with the file. The earthquake doesn't know what is the foundation type building have. So it is coming with the normal way. It is coming with the normal way. So this is structure, the energy disappeared. The resistance against the earthquake is much better because the mass is lumped somewhere above the superstructure, very close to superstructure. If you draw the center of the gravity of this one somewhere here, but depending on this high-rise building, so the center of the gravity will be coming much lower. The issue is this pile building will not vulnerable for the overturning. This is vulnerable for the overturn. But here it does not allow to perform a much higher base shear at this level because itself the raft also moving along with the building. Here the pile, there are two types of pile. One is the friction, other one is the bed socketing pile. Bed socketing pile, if there is, right? So the earthquake, for the earthquake, it doesn't matter the substructure, the superstructure, this is a unique structure. So it is creating the shear, base shear around including the pile. If the soil is lower, the soil is not stiff. If the soil is given enough stiffness, so it is starting somewhere here, right? So the biggest issue is the formation of the plastic hinge in the foundation, piling, especially can be even lower the foundation, but very rarely because we assume that the frictions and the lateral combinations comes through the buildings are enough to taken care of the earthquake load. That's why in most of the modeling in the MIDAS, right, earthquake modeling, so we prefer to model with the foundation, which we are not doing at the general software like SAP whatever the software, even the SAP you can do it with the spring constant, but need to be very careful. How do you give the spring constant? Because in earthquake it says, so the below the 3 meter to 5 meter in a pile, the soil condition has to be taken care of by the response spectrum sometimes. So then if you are not doing the, if you are doing the seismic analysis, so that is stiffness has to be given to the pile, right? But MIDAS, that's completely allowed because you are completely allow in the software itself to model the seismic separately. All right. So with these, I'm sure the flow to be designs, again, the earthquake has been discussed. However, the detailing and the designs much more, we can talk in another day. Let me quickly answer these few questions asked. And by the way, I would like to get your feedback. How was the lecture? And was it clear to you? And is there any place to improve? So let me know, right? You can put a comment. So the raft foundation, I was answering it. So is there any reasons why high-rise buildings are almost conical and the pyramid shape? The lower axial loads towards the top. So what if the non-conventional same such as the biochemical design? So it is encouraging non-conventional shapes in the earthquake. We know that any any structure, if we can find two directional, so this is XX, YY, we know that the second movement of inertia is playing biggest role. So the EI is stiffness. So in any direction, what we are putting the shear walls and etc., we put in the weaker axis. If we do have like a non-conventional shape itself, right? So that will be definitely support, because the wind doesn't know what is the most weakest axis. So that's come in every direction, right? That's why if you see especially in the world most higher, for example, let's take Burj Khalifa also. I don't know how many of you know the Burj Khalifa, the pile is not bed socketed. It is a friction. So then in terms of the lateral, forget about the earthquake, wind and the lateral, it is required to have a stiffness in each and every direction. That's why you see when it comes to the top, so the stiffness at the lower bottoms are much higher than the upper, right? Your next question is the conical and the pyramid shape. Now, I mean, I don't have clear answer for that, but there is another way of, I have seen the few articles, research article, that you can lump the mass around the perimeter, right? Around the perimeter, which definitely helps to improve the structural stability in the building. I am sure everyone knows why is it, because you know that the parallel axis theorem, right? If you take a parallel axis theorem, so let me take parallel axis theorem for the second moment of inertia. So IXX, right? So AY squared over IXX. So if the areas are massed to outer pyramid, it no need to be the shear wall, even the other elements which is resisting the twisting and the lateral forces. So that's why we always prefer to have this one. In the Europe, mostly the openings, at least one or two openings try to keep in between, because the energy dissipations. Now, for example, take a footprint of the building. What they are doing is they try to keep few opening, not in everyone, but some. If you try to keep the staircase and the elevators in between, so the shear walls are there, right? Here and here also, but the masses are lumped to the boundaries. So what will happen when the twisting actions come? The rotational stiffness is much higher, because it's depend on the distance to the neutral axis at the center of the gravity. If the central of the gravity is at the outer fibers. So that will be definitely help us to make a much stronger element. However, now, for example, country like us, we don't entertain this much. We are not be able to entertain this one because the investor wanted to have a higher area in each floor and they don't have a much higher land plots. Maybe we are working on 20, 30, 40 perch land. So they need to have a maximum number of the apartment. By the way, the other countries in the city or the peripheral, they have enough land. So they are going with this concept as much as possible. So this is how it's work. So let me go for the next one. When the modified compressional field theory is taken into the account, column can fail earlier with the lower ratio. How we can incorporate factor into the shear? Yes, of course. This is, I think, I'm sure this is quite a interesting question. Yes, modified compression theory is some things that you work with the movement curvature. So, right? So the move, wait 1 minute. Right? So the movement curvature when you are working, right? So this is the curvature phi and this is movement. So the movement, this is phi y and phi u ultimate and this is phi yield. So the movement is defined, the ductility is defined phi ultimate divided by phi yield. Right? So of course it can be pushed into this line because I think the question you ask, I can share with, find it out the ultimate curvature for the ductility has 4 different factors. One is the concrete can fail after the maximum energy absorption. So that is number 1, concrete failure. Number 2, the steel, the longitudinal steel can reach their maximum energy energy capacity, right? Third one is transverse reinforcement reach their maximum capacity. Fourth one is, so we assume the maximum peak movement. The sorry, this is actually very tough question and I don't think everyone can. So this is M max. So when it is lower down to 20%, it can be calculated the fail. So the section reach maximum 80% of the peak. So that is the number 4. So the modified compression theory actually in the world is still so many research is going on because we are not be able to model the fiber. We are not be able to model the actual behavior of that, the material, for example, the proper bond in between the steel and the concrete. So because of that, I think code does not provide any factor for this. What you have to do is you have to be always keep the axial load ratio lower. When the axial load ratio lower, of course, the volumetric ratio has to be properly put. It means the hoops within the section as described in the Eurocode 8, not the Eurocode 2. Then the section always will have a uniform stress, which is support for the ultimate curvature push longer. All right. So that is, I mean, code, it does. I think this is a research question that we can work on the OpenSeas very hardly. Right. So I think, is there any handbook for this one? I think Eurocode, that Seismic, there are certain guidelines that you can work on. What is the difference between time history method and the CESC? So that is actually 2 different analyses you have to put. Time history is that you have to work with especially the nonlinear analysis. So then it works with the iteration. So in the same time, you have to produce so many matrices. So then it will comes at the Excel file. Sometimes very rarely you get. So you can see in each and every load increment. let's say you apply 10 kilonewton, so you can have each 0.1 load increment. So with that time history, you can take out what is the displacement, what is the rotation, likewise. So when you work with the SAP 2000 or the general softwares, you directly give the 10 kilonewton. So you will get the last point only. So the maximum drift, etc. But anyway, the earthquake engineering, we need a nonlinear analysis so that you can find it out the capacity of the element, economical capacity. I was explaining you what do you mean by the dynamic load and the static load, because when you work with the general softwares, once again, you are not allowed to give the iterations. It means the load increment analysis. So the MIDAT is given. For example, you have a, so someone asked me to write a horizontal, but I'm writing on the screen. That's all. So you apply the 10 kilonewtons per meter. So software, when you apply this one, so the F is equal K delta in the force-based method. So he directly applied the 10 kilonewton. And he make a K stiffness matrix. That is, for example, if you give the grade 25, he already make it. So then he calculate the delta. Once he calculate the delta, F times K inverse matrix, right? Having these delta each and every node, software calculate what is the flexion and the shear. Because we know that the integration of the movement is a shear. Integration of the shear will give the displacement. So based on that, the software is working. If someone was, what will happen to this 1 kilonewton apply? Then the second step is 2 kilonewton. Third one is 3 kilo. Likewise, up to 10 kilonewton, you have to deviate with the iteration analysis. Nowadays, in any project, in the large scale project, we are looking for that. Because then only you can see how the elements are performing very well. The damping, it's completely on the another lecture. It is saying 95%, the 5%, 90, 10. So it's depend on the element type. So the damping, you can calculate either type of the structure the damping are proposed. I think initially you can work with the damping ratio, which is proposed by the guidelines and the code of practice, because it doesn't make much sense. I mean, especially in the if your structure is designed again the energy dissipated, I mean in terms of the ductility level, so the damping is not playing the bigger role. Damping is required if you are internal element, like if there is a column, beam, you have an infill, let's say the wall. So then this wall will definitely support for the lateral load because the load itself give the stiffness. But in our analysis, you know, except the shear wall, we don't do the brick wall modeling, etc. Am I right? So we just give the load for those elements. So then that's why we put the damping. Otherwise, you can count it. It is into the software as well. So with these, I think almost 1.5 hours, quite heavy stuff today. So I'm very much sorry about this horizontal writing, because I am writing on the, you know, the screen. Any questions you can direct to me. So my phone number is also here, right? So the WhatsApp, not calling at all. So thank you very much.
Yeah, Dr. Pradeep, thanks a lot. And I think it is rather than a webinar, it's very advanced lecture, I suppose. So everyone, I think, absorbed whatever you explained. Anyway, I will call Engineer Manduka Kurupu to deliver the vote of thanks.
Yes.
Manduka?
Yes. Thank you very much, Dr. Laksiri Pradeep, for the Civil Engineering Sectional Committee webinar on seismic design of buildings in Sri Lanka using Eurocode 8. It was a very interesting session and was very valuable for practicing engineers who are interested in using Eurocodes for seismic engineering aspects of buildings. We hope to have a continuation of this webinar series. Also, I thank the IESL Secretariat and IT team and the publicity department for taking the steps to publicize the event and for hosting arrangements. Last but actually not least, I thank you all for your active participation. Have a wonderful evening to you all. Thank you.
Right. Thank you.